All right, good afternoon, everybody. Thank you so much for coming. CS50 is super excited to introduce John Britton with GitHub today, who's going to give us sort of a deeper dive into the internals that underlie Git, the popular open source control software. CS50 uses Git for just about everything we do, so we're super excited to take a deep look as well. So without any further ado, John Britton with GitHub.
Thank you. Everybody? You shy? Too much pizza. All right, so just a brief overview of what we're going to be covering today. I'm going to walk you through creating a Git repository, the underlying data structures in Git, and the process of creating a commit and kind of how all that stuff works. I'm going to assume already that you already have some understanding of how to use Git. You'll be able to take something away from this no matter what, but it really will be building on the fact that you probably already know or have used Git before. So yeah, let's get started. We're going to be on the command line most of the time, just to look at things, and I'll be using the whiteboard a lot too. So Git is a version control system. The idea behind Git is that it allows you to track changes to your project over time. And that's useful for things like collaborating with others or finding out when bugs were introduced and reverting changes. And it's also really useful as a documentation system. If you've ever worked on a project that's been built by previous developers or something you did a few years ago and you don't remember why you did it, you can go back at your look at your Git repository, your history, and kind of use it as a way to remember the way you thought about things to find a solution. A really important attribute of Git and what makes it a very powerful version control system is the fact that it was designed to be distributed. And the fact that it's distributed is the reason why there are some things that don't always make perfect sense. If you've ever used Subversion or other version control systems, you might have noticed that they have things like sequential version numbers, 1, 2, 3, 4, 5. In Git, you have these long hash strings that identify versions or commit history checkpoints. And the reason for that is because Git is decentralized. So we're going to look at how Git was designed and the kind of the motivation for it as well. So to get started, I'm just going to create a Git repository. I'm going to say git init example. What this command does is it just creates a new repository on disk for us called example. I'm in my home directory, and this will create it in my home directory on my machine. You can see Git reports back initialized empty Git repository, and I can change directories into my new repository. Pretty good first step. You'll notice on the right-hand side that it says I'm on the master branch, and I'm in a clean status. What this is doing is my terminal, every time that I press enter, it will just run git status and report the status on the terminal for me. We can also check the status using the git status command. All right, you can see we're on the initial commit. And so we've got our repository created. The first thing I want to look at is the command ls. ls shows you what's in the directory. It looks like there's nothing. In the case of Unix, so I'm on a Mac. I'm using a Unix-based operating system. Files that begin with a dot or period are considered to be hidden files and are not displayed when you run ls. There's a command ls-h, which will show hidden files as well. Oh, ls-lah. There we go. Now you can see that I have a folder in my Git repository called .git. So this is the first kind of internal thing that we're going to look at. A Git repository is actually just a folder on your machine with a folder inside of it called .git with some metadata inside of that. It's important to know, like we said in the beginning, Git is distributed. So all the commands I'm going to run, unless I tell you otherwise, they're going to be local commands only. There's no network activity going on. It's just things happening on my machine. The way that it works is that as I make changes in my Git repository, in my project, those changes get logged and saved as files inside of this .git directory. Other version control systems have a client-server kind of model, where you have a centralized server on the network, and every time you make an action, you have to connect to that centralized server and communicate and coordinate between you and all the other clients. With Git, there is no centralized server. There's no backend process or daemon. It's all file operations in this .git directory. All right? Let's look inside of that .git directory. So I have a command called tree. Tree is a really nice Unix command. It just gives you an ASCII art tree structure. And I'll just do tree.git. And what you can see here is that there's a bunch of folders and files inside of the .git directory. In practice, you'll never need to use this. You should never mess around with this stuff. If you delete things in here, you can damage your repository, but it's good to know how this stuff works. So you've got some stuff in here. The two things we're going to be focusing on are down here, this objects directory and then this refs directory. So I'm going to use the whiteboard for this. I think this is probably something that if you used Git before, you're familiar with. And it's the concept of having a staging area. So you have 3 working, staging, and repo. So I like to think about it like this. The purpose of Git is to provide a version control system that allows you to track snapshots of your project over time. As developers, you're probably familiar with the working directory. You have your compiling tools, you have your home directory, you have your IDE, your text editor. There's a folder on your machine that edits files in the working directory, and that's pretty straightforward. And then Git layers on top of that 2 more kind of areas to think about as in your mental model. That's the staging area and the repository. The staging area, the way to think about this is like a rough draft. You work with your editor in your working area, put things exactly how you want. Maybe you make a new feature, you fix a bug, and as you make the progress there, you add it to your staging area to get it just right. When it's just right, you save it into your repository history permanently. So we have a couple commands. This is git add. So what git add does is it takes a file in your working directory and it stages it. It puts it into your rough draft to later be saved into your repository history. And then you have another command, git commit. And what that does is it takes the rough draft that you have in your staging area, which is a representation of a snapshot of your project exactly the way you like it. You can put things in, take things out, and then you run this git commit command, and it saves it into your repository as a permanent snapshot forever that you can then later share via the network to your collaborators or to GitHub. So I'm going to walk through these commands, and as I walk through these commands, I'm going to show you what happens under the hood. So to simulate writing some code, I'm just going to use the command touch. And I'm going to say touch readme.md. MD stands for Markdown. It's just a text file type that you can put text into. Touch creates a file on disk with no contents. So I did touch readme.md. You'll notice that my status has changed over on the right-hand side. And if I do ls in my current directory, you'll see I have a new file called readme.md. It's pretty straightforward. The file, if we investigate with cat, you can see there's an empty file. There's nothing inside. Git status reports that I have a new file that's untracked, and it says to use git add right there. So I'll say git add readme. Now at the same time as I'm going to do that, I'm going to open up another tab, and I'm going to cd example, and I'm going to do watch-n.5 tree.git. And on the right-hand side, this is just showing us the contents of the .git directory. Every half a second, it's updating. So whenever I do something that edits the .git directory, you'll see it happen on the right-hand side in real time. So when I run git add readme.md, what actually happens? Well, we said we have our working directory, which has the readme, that blank file, in the working directory that my editor can use. And we have this staging area, which represents a rough draft of my work. And git add copies the file. It's important to think it's not a move. It doesn't take it from one place and move to the other. It copies it over. So we use git add readme, and it copies it to the staging area. And when we do that, you'll notice that something changed in my .git directory. So this kind of furthers the proof that there's no network activity, there's no backend server. All we're doing is editing files on disk. It's in this hidden folder. There's a new object created. So this objects directory, it has a really interesting way of storing stuff we'll get into later. But I want to talk about the objects. So we have objects. There are 4 objects that Git stores. I'm only going to talk about 3 of them today, just for simplicity. But the first is called a blob. The second is a tree. And the third is a commit. The fourth object, if you're really curious, is an annotated tag, but we're just not going to get into that today. So when we did git add readme.md, what happened? Git conceptually took my readme file and put it in the staging area. But what it actually did is it took the file, looked at the contents of the file, took those contents and put it as a copy into a file in the objects directory, which represents a blob, which stands for binary large object. It's basically just a collection of data. Blobs don't have names. It's just the raw data. And then it took that raw data and a little bit of header information, like how long the file is, what type of object it is, and it ran it through the SHA hashing algorithm. And after that hashing algorithm, the hashing algorithm always outputs a 40-character hex kind of output, which is, in this case, E6, 9DE29, ... all that stuff over there. Oops. If we do this, make it a little bit bigger. So that's this. E6, 9DE, whatever, this whole line. And so it calculated that hash, and then it created a directory in the objects directory called E6, and then it took the rest of the hash and it used it as the file name, and then it stored the raw data, which in our case is the empty file. So it's a blob object of 0 bytes, and that was hashed, and that's where it came up with this E6 thing. So what that tells us is that every time you run git add, you're actually putting something into your objects directory. So that's on your local machine. Things are being saved. But what's important with Git is that we care about snapshots of the entire project. We don't care about individual files. So the next step, which you're probably familiar with, is git commit. Commit lets you create a kind of a checkpoint in time, a snapshot of your repository that references the entire working directory at a point in time. So let's do that. Git commit -m create empty readme. When you create a commit, you also provide a message. And now, again, watch on the right-hand side what happens. You can see that there are 2 more objects that were created. All right? Now, these objects are of the other types, tree and commit. Let's investigate. Let's look at these more closely and see what those objects are actually made of. So the first thing that I'm going to do here is do a command called git show. So git show is a plumbing command in Git. So broadly speaking, Git is divided into subcommands. They're called the porcelain and the plumbing. The plumbing commands are kind of under the hood. You don't usually use them that often. But other more user-friendly commands are made by stringing these together. A common example is the command git pull is actually 2 commands, git fetch and git merge, together. So in our case, git show, it allows you to look at an object. So in my case, I'm going to look at our first object, which is the blob. Git show E6 D7 BA21. And I don't have to type out the whole thing. I can just type out the shortest unique identifier for it. Maybe I typed wrong. Git show E6 D7. Oh, I'm sorry. Yeah, you're right. Thank you. E6 9DE. E6 9DE. There we go. OK. All that work for something very interesting. It's an empty file, right? Like, we kind of already knew that, but like you can prove it by using git show. It shows you that that object is actually, in fact, an empty file object. An empty blob object is more appropriate. So let's show the other stuff. Git show, and this time I'll type it correctly, 6D D7 BA. So what object is this? I have no idea. But Git tells me. It's a commit object. It tells me what the commit identifier is. It tells me the author, that's me, John Britton, the date it was created, the message, and then this is not actually stored in the commit. This is just kind of a reference of like what was changed by, this was computed. So it shows that I added a new empty file. So let's check out the third. Git show F9 3E3. And you can see here there's an object called a tree, and it has 1 item inside. Now these git show commands are pretty raw. They're not showing you, they're just showing you like a basic overview. We can get more detailed with this as well. So in the case of the commit, I can say git show dash dash pretty equals raw, and this will give us more information. Again, you don't need to know this, but it's good to inspect these things. So I'm going to go ahead and say 6D, D7, BA. Right? OK, there's a lot more information here. I'll point with this so that it's easier. So first you have the commit, again. Then you have the tree. So this shows us that when we make a snapshot, when we do git commit, what we're doing is we're creating a moment in time that says this person created a snapshot with this message, and that snapshot is represented by this tree. A tree is just another way to say directory. This is a tree that represents what your working directory looked like at that point in time of your project. So there's the tree and the pointer of the tree. You also see that there's an author here and a committer. This is something that catches people sometimes. The author and the committer, why are they there twice? The author is the person who actually wrote the code. The committer is the person who saved that change to the repository. As Git was actually created for the Linux kernel development, it's pretty common for somebody to author changes, send a patch file to a maintainer, and then the maintainer commits it. So it allows you to track those two things independently. And then you have the message. There's another command that I'll show, which is git ls tree. This is a way to look and inspect tree objects and see more information of what's inside them. So I'll say F9 3E3. And in this case, let's try it again. There we go. You'll see that there's a few different parts of this tree. First, it has the number 1, or 100, which means this is a regular file. 644, you might recognize this as Unix permission. 644, 755, 777, like those kinds of things. This is the permissions of the file in the project. So Git actually version controls the permissions on disk as well. So if you edit the permissions of a file in your project, that's considered a change in Git, and it will be version controlled. Then what type of object does this tree reference? So we're looking at what's inside the tree. This is a list of all the items, ls. So we have one regular file with 644 permissions, which is a blob object. And the blob object is referenced by this hash, this unique identifier, E69, so on, so on, so on. And then lastly, it has the file name. And this is very interesting. The file name of the file is not stored in the blob object. It's stored in the tree. Think about why that might be. What happens if you have multiple files that have the same contents? With this system, you're able to have multiple files with the same contents, but Git only stores at one time, even if they have different file names. What happens if you change the name of a file? Should you duplicate that data when you change the name of a file? No. With Git, all you do is you create a new tree object which has a new file name. The object in your objects repository that represents the file, the blob, doesn't change. So file name changes don't actually affect the raw data. And so what this means is that we're able to really easily rename files without a high cost. So this is what's inside of a tree. So we've been able to inspect those 3 different objects. Yeah, go ahead.
So when I change a file, Git will usually delete the file and then show it as a new file being created. Is that inconsistent with what you said, or is that evidence to it?
So the question was, when I delete a file, Git will show that as a new file that was deleted. Is that what you're saying?
Yeah, it'll say you deleted. If I have file A and I rename it to B, my computer will say deleted file A, created file B.
Yes. So so the question was about what happens when I delete a file. So say I have a repository and I have a file inside, and I delete the file. What happens in Git is Git says, this file was expected to be here. What you need to do is you need to use git add, to stage the fact that you deleted the file. You need to tell Git, my rough draft should be updated such that the file is no longer in my rough draft. So you do that, and then you commit it. And when you make the new commit, what happens is the new tree for that commit will have one less entry in the list.
Sorry, no, what I was saying is I don't delete a file. I just rename a file and show it as you
deleted
the file
and added a new one.
Added it, but it sounded like what you were saying was that Git will track name changes, which is not what my experience.
No, it doesn't actually track the name change. So the question was, if I rename a file, Git shows it as a deleted file and a newly added file. Under the hood, what I'm explaining is that when you rename a file, what happens is that there's a blob object that contains all the data that that file possesses. So say you have a 5 megabyte audio file in your repository. All the binary data in there is stored in an object called abc123. And then there's a tree that references it as like intro.wave or intro.mp3, whatever that file is. If you change that name, the blob object, there was no data in that blob object that was modified. So what will happen is in the tree, a new tree will be created with a pointer to the same blob object and a different name. Now, what you're seeing reported about in the status output, that's a totally different control thing. And there's actually a feature of Git that allows you to detect when a file is renamed. But under the hood, the way it's stored is what I just explained. I hope that answers it. I'm also going to take some more questions at the end that I can like do some demos of that too. Yeah, go ahead.
If you do a git mv instead of just a normal mv, then Git will be aware that you're moving.
So there is a git subcommand. What the comment was is there's a git subcommand called git mv. So just do git help mv. This is a git move command. It basically does your operating system move, and it also manages your staging directory or staging area for you as well at the same time. So you don't have to do the add command separately. All right, so to continue, we have 3 objects. So one is a tree, one's a commit, one's a tree, and one's a blob. And so we have our first bit of history in our project. I'm going to pull up a command called git k. If you have Git installed, git k should come with Git for you. It's a GUI tool, and it gives you a visualization of your repository. So it's pretty basic right now. Our repository is very simple. We just have one commit. Here's the commit. And if we click on it, you'll see it has the message, and then down below you have kind of some information about it. What I want to drive home here is that when you're thinking conceptually about Git as a user, you don't think about trees and blobs. You just think about commits. You think about, I took a snapshot, I took a snapshot, I took a snapshot. I want to look at this snapshot. I want to go back and look at that snapshot. I want to merge these 2 snapshots together. I want to create a branch and work on the side. You don't think about the trees and blobs, but like this course, this talk is about the internals. So you don't see any of the complexity of like the blobs and trees and stuff on here. So we have one commit, and I'm going to point out this thing called a branch. When you create a Git repository, you get one default branch. It's called master by default, and it doesn't mean anything special. What master is, as a branch, is it's just a pointer. It's a pointer. It's also called a reference to any commit in your repository. Think about it as a bookmark, a tool for navigating around your repository history. And I'll show you where that's stored as well. So if we go into our .git directory on the right side, you'll see here there's this directory called refs for references, heads, and one called master. This is by default. If I go in here and I say git, or if I do cat, which just shows the contents of the file, refs, .git, refs, heads, master.
John,
yes?
can you clear so we can
Sure.
move it up?
Like that? It's better. So I'm just going to do cat.git refs heads master, and that will show you what's inside that file. Can anybody guess what's in there?
A SHA.
A SHA. Thank you. So this is the hash of the commit that master references. So master is a bookmark that points to a commit. We only have one commit, so it's obviously the one that we just created. But it serves as a kind of a navigational tool for you. If you've ever heard the term being on a branch, being on a branch just means that when you make your next commit, that branch will be updated to point to that new commit you just created. It will be advanced. Conceptually, people think about branches as like a divergence. You go in 2 different directions. That's the wrong mental model for Git. It makes sense that you're doing some work off on the side, but actually the mental model you want to have is that a branch is just a pointer, a bookmark, to somewhere in my repository history. So as we get into more complex history, you'll get to see how this works a bit more. I want to pause for just a second and see if anybody has any questions on the stuff that I've covered up to this point. People seem to be mostly coming along. Yeah, go ahead.
I think I get it, but just generally, blobs seem to be related to git add. Commits obviously do commit, but a commit is pointing to a hash, which is pointing to a blob. And where does the tree fit in there?
Okay. So the question was about, git add seems to be related to blobs. Git commits seems to be related to commits. What I want to emphasize is that git add is really the main thing to think about with that is the staging area, creating your rough draft. You can put things into the staging area and get it ready. Every object has a hash. Okay? So a hash is just the identifier. And the reason, so I mentioned at the beginning of the presentation about Git's distributed. One of the challenges to overcome with a distributed system is how to reliably give things identifiers without communication. So what we have is with the SHA hashing algorithm, we have a deterministic way of creating an identifier for a particular object without communicating. So in the case of a blob, any data that we're storing, we take the contents of that data, that file, and we run it through the algorithm, and that's where we get the identifier. In the case of a tree, we did git ls tree. We did this command before, git ls tree. Think about what we said before, that the object identifier is a SHA of the contents of the object. So the object identifier of this tree, f93 ... that object identifier is actually a hash of the contents of the tree, which is the list of items in the tree. So this right here, this data, is what we took and we hashed and created an identifier. And what's interesting is this data includes the hash of all the blobs and trees underneath it. So if any one bit changes in any file, any subdirectory, then the identifier of the tree will change. It will be different. And it will be drastically different because of the way the SHA hashing algorithm works. And then with a commit, you take the staging area, which has like kind of a prepared tree, a rough draft of your working directory that you want to save forever, and you create a new object. That new object, show this. That new object has an identifier right here. That identifier is calculated by the contents of the object. The contents of the object includes the tree and the hash of the tree, and also all the other stuff. So what it means is that if any bit anywhere along the line, including all of this author information, the messaging, you'll get a different but deterministic identifier for the commit, and that's really important. Does anybody know what that data structure is called? Where you have like kind of like way down at the bottom, one thing changes, the hash is going up. It's a hash tree. I think also a Merkle tree is another way to say it. So that is the kind of core concept of Git that allows you to be distributed using those kinds of things. Because otherwise, we would have to communicate about what our identifiers are. So yeah.
How did you set your terminal to give the branch and the...
That's a good question for after class. I would be happy to talk about my terminal after class. We have a tight timeline, though, so I don't want to get into that right now. Any other questions before I move on? Just making sure, I want to make sure everybody's following along and coming along with us on this stuff. OK, so we've made our first commit. Let's start talking about multiple commits. All right. So what happens when I create a new file? Let's say touch new feature.rb. So I'm a Ruby developer. I make a new feature. Just create a new file. Maybe I'll do atom new feature.rb. I open up my text editor. I say class new feature end, def foo puts bar, right? Some simple code. Git status. There's a new file that's untracked. Again, we follow the same kind of pattern. Git add new feature. And on the right side, you see one new object pop up. It was somewhere down here. Then we do git commit -m, add new feature. All right, and now it's committed, and two more objects popped up. If I do git k, let's look at this from the perspective of just commits. The first commit existed before. The second commit is a new commit. Master is updated. That pointer, the bookmark, now points to the new commit. All right. If I go in here and I do cat.git refs heads master, you can see that it's this new identifier. If I do git show, I normally would put an object identifier here. Normally I'm typing in these hashes, but now we know master is just a pointer, and since we were on the master branch, we made a new commit. That pointer points to the newest commit. So I could say git show master as shorthand for git show 99fba, whatever. I don't have to type that all out. So you can see that there's a new commit. It says add new feature, and it shows me a diff. I can do git show -- pretty equals raw master. And this is where we see the additional details. And what I want to point out here is there's a new entry. This new entry is the parent. So when we create a commit, It includes all the data about all the blobs and trees and stuff that are in there. It includes metadata about who authored the commit, when it was authored. It includes a message, and it includes a reference to its parent, so the commit that came before. A lot of times people think about it as, a lot of times people think about, like, why don't I have a pointer going the other way? What's the next commit? Like, if I go from the back going forward. Well, because all these objects being blobs, trees, and commits, all of these objects are immutable objects. They're stored in your objects directory. Once you create them, they can never be touched. We couldn't possibly go in and add a pointer to the future thing, right? We couldn't add a pointer to the new commit that we created. We'd have to know about the identifier of that commit before we even created it. It'd be impossible. So in this case, what we do is we just create a pointer going back. What's also interesting is because the pointer going back to its parent is included in the commit object, the identifier of the new commit object is unique and, in a way, based on what came before. So if you imagine we have two parallel universes, we have two projects. One project where I create a README in the main folder of the project, and I create a commit. Another project where I do two commits. I do first commit with an empty README, and then I create a second project with put in all the same contents. Even though everything we did in the second commit is the same, because there's a history, even if we did it at the same time with the same author and everything identical, because there's a history there, the one with two commits, the first and second commit identifiers would be different, right? Even though the sum of the work is the same. So that makes it so that in a distributed system, we could all be on a team together. We could all clone one repository, and we could all do the exact same work, and we would all end up with unique commit identifiers, right? However, if we did all exact same work, and we all created this 10 megabyte file that was in our reference somewhere in our repository, we all did it, and then we all synced with each other, we would never transfer that 10 megabyte file because they would all have the same hash, and our communication between each other, we would know that because we have the same hash, we have the same file, we don't need to transfer that. All right? Does that make sense? Yeah? Cool.
So
yes?
if I have file a.text and then I change something, that commit will be associated, like the delta is a new blob?
That's a great question. So the question is about, I think what you're getting at is, when I make a change to a file in my project, does Git store the changes, or does Git do something else, right? So if we look at our structure, we have commit points to a tree. The tree points to blobs and other subtrees. There's no reference in there of a diff. We don't store diffs. If you look at Subversion, Subversion stores diffs. And at first glance, that might sound like a smart idea. We can store diffs because they take up less space, right? Like it's just like, oh, I only changed one line. If I have a 10 megabyte file and I change one line, now I have to duplicate the 10 megabyte file, right? And that's actually how Git works under the hood. We do duplicate things. If you change one bit of a file, you get a total new object with that data duplicated. However, if you think about computational complexity, if you're using a Subversion repository and you want to check out, you want to get a version of the project, how do you get the version of the project? You go through the entire history and you sum up all the diffs up to that point, and you have to do a calculation. That calculation has n parts, n being the number of commits in your history. With Git, it's an O1 operation. You just go to the commit and you pull it out, and it's a perfect reference already made. If you want to compare 2 points, you can do a computation to compare point A and point B. Right? That's how Git works in that situation. Others have questions on that stuff up to this point?
So the size of the repository is basically roughly the size of your total files times the number of commits.
So the question is, what's the size of my repository? Is it the number of commits times the amount of files I have? You would think that because I just told you that this is the way we store it, but there's really an intelligent layer in Git. I won't get into mucking around with the commands today in that, but there's a compression layer. So what happens is you have this objects directory, right over here. All of these objects, each one is unique. It represents a unique blob tree or commit. However, when you have a lot of blobs that are mostly similar, say you edit one character each time, Git is smart enough to take all those blobs together and run a compression algorithm on them and put them into what's called a pack file so that you don't end up wasting space. Actually, it's possible for projects to have their entire Git history be smaller than one checked out version of the project. So like something like a huge, huge operating system, which would have hundreds of megabytes, maybe gigabytes of source code files in one checkout. In a Git repository, it could be smaller than that because of the compression. That's a very good question. All right. So now what I want to get into is a bit more about branches and how that works. So we learned about refs, heads, master. We learned that branches are just pointers. And as we make commits, those pointers get updated. So we'll make another commit, and we'll go in and say, let's modify a file. Or let's make another new file. So in here, we'll say touch new feature 2.rb, git add new feature 2, git commit -m, add another. Obviously, like, this is not great practice to just write this kind of commit messages, but this is just for demonstration. I don't actually write code like that. So git k. So now we have another commit. Our pointer points to that. There's a command. I'm going to draw this on the board also. So far, we've only gone in one direction. You take stuff that's in your working area, you put it into staging in your rough draft, and then you save that as a snapshot into your repo. So we've got something like this. We made our first commit, which was just an empty README. Then we added a new feature. We made a second commit that had a pointer here. Then we added a third, new feature 2, and that points here. And now we have a pointer here called master. Right? Now, if you want to look at all three of these areas together, what's in my repo, the latest thing there, what's in my staging area, what's in my working area, they're all equal. So what's a command to compare these things? Does anybody know? Git command to compare. Diff. All right. So git diff. If you use git diff, you can actually compare what's changed. But a lot of times people use git diff without knowing what it's comparing. So when you run git diff, what do you think you're actually comparing?
Repo to working. Repo to staging.
Repo working versus staging.
All right, so let's try it out. So right now, I have git diff. Right now, there are no differences. If I touch a new file and I run git diff, I have to actually, let's not use that as an example. Let me do this. Go in here. Example, edit, git status, git diff. So I edited a file that's already in Git, and you can see that something changed. Now, what's happening here is it's comparing what's in my working area with what's in head, or the latest thing in the repo history. If I do git add, I'm sorry, new feature 2, git diff. Sorry, with the staging area. It's sometimes confusing for me too. So it's comparing what's in the working area with what's in the staging area. So it's basically saying there's a new line in the working area that's not in the staging area. Then I ran git add, and now when I compare them, it says there's no differences. So even though my repository doesn't have that edit that I made, it shows git diff shows no differences. The other command that we haven't seen that goes the opposite direction here is git reset. So git reset lets you take things out of your rough draft. So I say git reset, new feature 2, and then I run git diff. Now it says, we have this one line in our working area that's not in our staging area. And I can re-add it. There's another command, git diff -- staged. So this is where I was getting to. Git diff -- staged lets you choose what you're comparing. So now instead of comparing your working or staging, you're comparing your staging area to your repo. So you can go, so you can do diff would be here, and then diff -- staged would be there. So you can see what's in all these different areas. And one of the things that we said was really important about Git is being able to go back in time, right? So how do we go and get what was in our history before and what actually happens under the hood. So I'm going to just run tree in here, and you can see my project has 3 files. It has an empty README, it has a new feature which has some code in it, and it has an empty, well, it has this new feature 2, which has some examples in it, which I'm going to throw away. Let me open up Atom. I'm just going to go ahead and delete that. So if I say git status, I'm git reset new feature 2. There we go. I'm all clear. I've got those 3 files. And I have 3 commits in my history, which I can see with git log. So if I go through git log, you can see 1, 2, 3. Now, one of the things that we said was really good is that we can go back in time and look at what happened in the past. So there's a command git checkout. What git checkout lets you do is specify a commit, a snapshot of your project, and update your working directory to reflect that project. So on the right side, I'm going to close that, and I'm going to run instead watch-n 0.5 tree dot. So this is the list of files that are in my working directory, updating every half a second. Okay. If I do git, I'll do git log, and I'll go back to my first commit. I'll just grab this. If I say git checkout and specify the commit identifier of my first commit, what happens in my working directory? All the other files disappear. So what Git is actually doing under the hood is it's going into that history, finding that commit. That commit's referencing a tree. That tree references subtrees and files, or blobs, and it takes what that subtree, or that tree under the commit represents, and it makes the working directory on my machine look identical to that representation, to the snapshot in time. That's really scary for some people, because basically it just deleted all my code. Right? It just deleted all the code in my working directory, and like I don't know what's going on. So it's not scary, because I can use git checkout master, and it all comes right back. Yes?
So if I'm understanding that, it's doing that from the .git directory, which is in
local.
Right, but that's in your project working directory, isn't it? So is that immune to whatever's going on with that?
Yeah, so that's a good question. So the question was, I understand that this is coming from, all this data is coming from the .git folder, which is a hidden folder storing all my Git history. But that also exists inside of my working directory. So is it immune to those changes? I would say, yeah. The way that works is the .git folder is special. So you can't add the .git folder to Git. That would be like, kind of meta, just be an infinite loop of objects representing themselves over and over again. So yeah, Git is smart enough to know not to mess with that. Basically, it's everything but the .git folder gets messed around with. And actually, there are some under the hood. I don't want to misspeak because I don't know the exact details of it. But under the hood, there are some like performance optimizations that happen on some operating system where there's like basically rather than hard deleting the files and moving the files and copying them, it's using hard links so that it can be really, really fast. So that operation of checkout can just be boom, like so. But I don't know the full details of that. Yeah, in the back there's a question.
What about untracked files?
What about them?
When you do a checkout or...
Okay. So the question was, what happens to untracked files when you do a checkout? Git tries to be smart. It will never throw your work away unless you explicitly tell it to with a command like force or something like that. If there are untracked files in your repository and Git can do its job without impacting those files, it will just do it and ignore them. If, for example, you have an untracked file that has a specific file name and a different version of your code has that file name and you're trying to check that out, it'll throw an error. It'll say you can't do that. There's a conflict. And it'll make you move it out of the way or use git stash or something to that effect.
So git rm doesn't remove blob representations of a file in previous commits?
No. The question was, git rm doesn't remove, does git rm remove the blobs from previous commits of a file when you do git rm? And no, it doesn't. What it does is it removes it from your working directory, and it adds the deletion of the file to the staging area. So if we think about the working area and the staging area is a copy. So when we add a new file, we copy it over to the staging area. But if we want to delete a file, we have to copy the deletion over to the staging area. So I'll demonstrate that because that's kind of a tricky one that people don't always get. So in my case, first git status, we're all clear. I can do ls. There's 3 files. I'm going to delete this new feature 2. So there's a command git rm, and I could use that. But I'm not going to because that's a kind of a compound command. What it does is a few different steps. So I'm going to do each step. I'm going to use my operating system rm command, new feature 2. I'm going to delete it, and I'm going to run git status. And what you see is that Git reports that the new feature 2 file was deleted. But it will say changes are not staged for commit right here. Changes not staged for commit. Use git add rm file to update will be committed. So my editor, my command line, my IDE, all that stuff just operates on the working directory. It doesn't know anything about version control necessarily. They might have like add-ons, but like broadly speaking, they're just working on your working directory. So when I deleted it, I removed it from the working directory. And if I do git diff, what happens is it'll say your working directory deleted the file, but it exists in the staging area. So what you need to do, and this is counterintuitive, is you need to add the deleted file to the staging area. So what you do is git add new feature 2.rb. Git status. Now it says changes are ready to be committed. You deleted file new feature 2.rb, and that's in your staging area. So when you make a commit, the new commit, the referenced tree of that new commit, will no longer contain new feature 2. You look very confused by this.
No, it's just a counterintuitive syntax.
Yes.
You're basically adding the negative.
You're adding a negative object.
Status of deleted, right? So you're basically adding the updated status of deleted to the staging area.
You're adding the change you made to that file, which in this case was
It's an attribute which basically says to delete it.
So I can use git reset new feature 2.rb. Maybe not. Git reset. No. I can do git checkout dash new. So yeah. No. Okay, I don't know how to do it. I forgot. Anyways, I could get that back, and if I used git rm, what I wanted to demonstrate was doing git rm and then the name, like if I use new feature, what'll happen is git status, it moves straight to this deleted status. So if you use git rm, so git rm makes it simpler, so it's like more logical. You just do git rm, it deletes it from your operating system, and then it stages it all in one step. So that's the logical thing people do. The reason you need to know about the git add a negative file is, like, say for example you use a build tool, and the build tool like accidentally checks some things in, and then it removes them, but like they're showing up as deleted files, but they're not staged. You need to know how that works. Yeah. So let's. I'm going to use the command git reset --hard head. What this does is it basically says, throw away everything that's not committed and go back to the latest version of the stuff you were working on. So I'm just going to go back to the point where we were here with 3. So yeah, we learned about checkout and how it works and how it updates the working area. We learned about the structure of a commit, blobs, trees, and the commit objects themselves. And we learned about how commits are related to each other via like a parent relationship, and there's a pointer that goes through all of these things. The like really important thing to take away from all of this is that every bit in Git matters. Like every single bit down to the very bottom finest grained thing impacts every other thing. So sometimes people will ask like, oh, I committed this really large file to my repository. Can you remove it from my history? And the answer to that is yes, but what happens is when you remove something from the history, then, like we said, all these objects are immutable. So the only way to remove something from the history is actually to create new objects that lack the thing you want there and use those objects instead. But by definition, the way Git works, all of those objects are going to have new identifiers. So basically what you do is you rewind history, and then you rewrite history as if the thing didn't happen. So I'm going to show you how that works. So we have git log, and we have 3 commits in our history. Let me do like a couple more. ls Adam new def bar puts foo git add new feature git commit -m add bar method, and then go back here, and then I'll do one more def baz puts baz git add method. All right, so I'll use get k. I did that so I'd have more commits to work with. So say, for example, we're in this situation. We have all these commits, and there's this file called new feature, and you really just want to remove it from all repo history. How could you possibly do that? Well, what you can do is use this command called get rebase. And what get rebase does, conceptually, is our situation is this now, and master is here. And so what we need to do is we need to go back to the first commit where that new feature was introduced, which I think was this one. And we need to create a parallel universe where there are different commits. And each one of these commits references the one before it. And this one references the original commit. And say this is A. We'd call this A prime. And B, B prime, so on and so forth. And what we need to do is go back through history, grab these, and create new commits that lack the features that we want to remove. So I'll show you how to do that. So there's a command get rebase, and what it takes is an argument of the commit to go back to in your history. So get log. We're going to go back 1, 2, 3, 4 commits, and there's 5 in the history. So we'll do get rebase -i head tilde 4. What that means is go from where we currently are, our currently active thing, go back 4 commits from now.
Can you use just dash?
Excuse me?
Can you use just dash?
Yes.
With it?
The question was, can you use just a hash? Yeah, this is a shorthand, so I didn't have to copy and paste that big hash or look it up. I could also do, master, tilde 4. I think I want 3. But anyways, it's the same thing. This is what's called a commit-ish in Git terms. Basically, it's something that represents a commit ID. So you could parse this into look at master, go back 3 steps, get the commit ID of that, and substitute. So I'll do that, and it will open my editor, and it will give me a list of things that happened. So it'll give me all the commits. So there's actually I did choose the wrong number, so I need to go back to 4. So here we go. First, we have add new feature. I'll use this one so the streamers can see. We have add new feature. That was one commit. Then we have add another new feature, which we want to keep. And then we added these 2 methods to that first feature. So what we want to do is essentially get rid of those commits, rewrite history, and just remove them. You could modify each individual commit. Like say I did a bunch of other work in those commits. That's a little complicated for a quick demo. But what I'm going to do is I'm just going to delete this commit, delete this commit, and delete this commit. And I save the file, and I close my editor. And what you'll see is down on the bottom, it had a quick, it said rebasing 1 of 1 down below. And now if I run git k, what you'll see is I only have 2 commits. And I have my README, and I have my new feature too. So my new feature file is just gone, deleted from the repository. However, the new commits that I created, so I only have A and A. I now have A prime. So I have the original commit and A prime. All those other commits I just kind of threw away. Just a second, I'll get to you. So we were able to remove that stuff. However, all of these, if I do git log, my first commit, which was just to create empty README, that commit identifier is the same as it was before. Nothing changed. But this new one is a totally new commit. So if we go into our objects directory, what we actually have is something like this, where master no longer points there. And we have basically just master here, just pointing at that. So what's interesting, and you'll notice I didn't delete those commits from the whiteboard. I didn't erase them. That's because they still exist on disk in my machine. They're not referenced. So after some amount of time, which is configurable in the advanced kind of config stuff for Git, they'll be garbage collected. Also, if you do a network interaction, they will not be transferred in a network interaction because they're not referenced, they're not useful. But because Git's a version control system, it wants you to be able to recover from mistakes. So say, what if I made a mistake on my rebase and I actually deleted the wrong file, and now my repository history is gone? Well, Git has this really handy thing, and this will be the last thing that I cover before we wrap up, which is, I like to call it version control for your version control. It's the ref log. So what it is a version history for each of the references in your repository that tells you what the status of that reference was. Okay, so in our case, we have a master branch, and previously the master branch was here. The master branch is not one of the core objects. It's mutable. So if I copy this repository to GitHub or to a colleague, they'll have their own master branch that can independently be pointed to something else and move around as a bookmark within their repository. All of these objects are immutable and will be the same and can't change, but these can be changed. So Git keeps a history of every state of all of these refs, and that's called the ref log. And so if we wanted to undo the rebase, which would essentially say, move this back here, like this, the way to do that is with the ref log. So I'll demonstrate that, and then we'll wrap up. So if I do git ref log, you'll see here the history. I did a rebase finish, rebase pick, rebase start, and then this is where I did, the last place where I made changes was this head at 5 with these funny brackets, which is when I added the baz method to my class that had the code in it. So I'm going to take that, and I'm going to go to my command line and do git, and keep an eye on the right-hand side here as well. Actually, I think I can do this at the same time too. Let me do git k. So I'll put this here. And what's this? I'll put this here. And so you'll be able to see all of this update at the same time, I think. So git reset -- hard head at 5. So what this is saying is take my master branch and put it back to where it was 5 steps ago in its history. Okay? And what you'll see is my file called new feature will show back up on here, and the commits that I deleted. So this commit will go away, and the other 4 commits that I deleted, or 3 or 4, whatever it was, will come back. So hopefully this works. Okay, it showed up here. I think I need to run git k separately. This doesn't update real time. Yeah. All right. So now we've undone the rebasing, which was mucking around with our history. And if I do this one more time, and this time just do 1, I can undo the undo, which will put us back where we were before. And then I can go here and say git k, and now we're back. All right, so that's everything. Thank you all very much for coming. Cheers.
There's pizza left in the front pod if you'd like to grab some on your way out. But this was Git Internals with John Britton, so thanks a lot. Thank you.
So, I think we have time for questions now after the stream ended. So I'm